Non-renewable energy resources. Most of the electrical energy produced in this country is generated in power stations that use non-renewable sources of energy. The Earth's supply of fossil fuels, oil, coal and natural gas, is limited. These fuels took millions of years to create. Once they have been consumed, they cannot be replaced. Nuclear reactors use uranium or plutonium. The supply of these fuels is also limited. The length of time that non-renewable fuels will last will depend upon their rate of consumption. This is controlled by world demand, their efficiency of use, and the development of alternative renewable energy sources. Using non-renewable energy resources. When fossil fuels are burned, they release heat energy. The heat released is used to generate steam. The steam drives a steam turbine, which in turn drives a generator, producing electrical energy. The electrical energy is distributed around the country via a system of cables and pylons called the National Grid System. Energy loss at power stations. Even at high voltages, the generation and distribution of electrical energy is a very inefficient process. The Sankey diagram shows typical energy losses for a fossil fuel or nuclear power station. Carbon dioxide. Burning fossil fuels releases carbon dioxide into the atmosphere. For the same amount of energy produced, burning coal releases more carbon dioxide than oil, which in turn produces more carbon dioxide than natural gas. Carbon dioxide is a greenhouse gas, the build-up of which leads to global warming. In addition, burning fossil fuels can release sulfur dioxide, which contributes to the formation of acid rain. Nuclear power stations. Nuclear power stations use the energy released during nuclear reactions to generate heat. Coolant, circulating around the reactor, transfers the heat generated to a heat exchanger. Here, steam is produced, which drives a steam turbine. This, in turn, drives an electrical generator. The uranium and plutonium fuels used in nuclear reactors are again non-renewable, as they are limited in supply. Calculating the current in the cables. The current flowing in the cables can be calculated by using the equation current equals power, watts, divided by voltage, volts. The electrical energy is generated at the power station at 25,000 volts and stepped up to 400,000 volts by the transformer before transmission to the grid. Renewable energy resources. At present, fossil and nuclear fuels provide most of our energy. Their supply, however, is finite, and they will eventually run out. In an attempt to conserve our supply of fossil and nuclear fuels, many renewable energy resources are now being developed. A renewable energy resource will never run out and will be available indefinitely. Many of these renewable resources owe their origin to the sun. The sun delivers heat and light. This warms our atmosphere, creating rain, wind and waves, and also provides the energy for photosynthesis. Other renewable energy resources do not originate from energy supplied by the sun. These include geothermal and tidal energy. In the future, they could possibly include nuclear fusion. Geothermal energy originates from the hot inner core of the Earth, which is fueled by nuclear reactions. Tides are produced by the ocean's gravitational attraction to the moon and sun. Renewable energy resources such as wind and water can be used to drive the turbines directly. Wind power. Wind power uses the kinetic energy available in the air molecules of the wind to turn giant wind turbines, creating electrical energy. The wind turbines must be placed in exposed regions, often on hills, where the wind is likely to blow frequently and strongly. The energy output of the turbine depends entirely on the wind blowing. If there is no wind, there is no energy output. Even when energy output is at a maximum, Hundreds of wind turbines would be needed to replace a coal-fired power station. Wind turbines produce no chemical pollution, but are noisy, and many people believe they cause visual pollution of the environment. Wind turbines are costly to erect, but have no fuel and low maintenance costs once in operation. Tidal power. A tidal barrage can be used to convert the gravitational potential energy of raised waves into electrical energy. The barrage is constructed across a river estuary and contains several turbines. As the tide comes in, the turbines rotate, creating electrical energy. The water level behind the dam rises, and energy is stored as gravitational potential energy of the raised water. The water can then be released through the turbines, generating more electrical energy. Wave power. Mechanical floats bob up and down in the waves as they pass. This up and down motion can be made to drive the electrical generator directly. The power output from each float, however, is quite small. This means many will be needed to generate significant amounts of energy. The floats cause visual pollution and can be a hazard to shipping. Power output will also be variable, depending on the height and speed of the waves. Tidal barrages produce no atmospheric pollution. However, they do cause visual pollution, and flooding can destroy natural habitats. Building a barrage is costly, but there are no fuel costs, and maintenance costs will be low. Possibly the greatest advantage of barrages is that they have the potential to generate large amounts of reliable energy. Hydroelectric power. The sun provides heat energy, which heats the oceans, causing evaporation. Clouds form, producing rain. Where this rain falls in mountain regions, the water can be collected in dammed river valleys. The water can then be released from a reservoir through turbines, creating electrical energy. It is also possible to construct a lower reservoir to collect the water after it has passed through the turbine. This water can then be pumped back into an upper reservoir during the night when the demand for electrical energy is less. This pumped storage system is extremely useful when providing electrical energy quickly in times of high demand. Hydroelectric power stations have no fuel costs and produce no chemical pollution. Capital outlay is high, and the construction of dams causes considerable environmental impact. Flooding can destroy natural habitats. Geothermal energy. Nuclear reactions deep inside the Earth generate great heat. In some places around the world, rocks heated by the core are found close to the surface, several kilometers. Cold water is pumped down onto these rocks, and the steam produced is returned to the surface. The steam is used to drive turbines and generate electrical energy. The main drawbacks of geothermal energy are the high capital costs of drilling several kilometers deep into the earth and the fact that few places on Earth are suitable. Solar energy. The sun provides heat and light energy that can be harnessed directly. Solar panels contain water flowing through pipes that absorb heat energy directly from the sun. The surface behind the pipes is painted black. Solar cells convert light energy directly into electrical energy. They are used to provide energy for calculators and communication satellites. Solar furnaces use many mirrors to focus rays from the sun to a point. This creates very high temperatures. The heat generated can be used to produce steam to drive generators. Solar energy is obviously more useful in places where the sun shines continually, like space. The energy absorbed will vary so that the energy source can be unreliable in cloudier climates, and of course no energy is absorbed at night. The initial capital costs can be high, but maintenance costs are low. Biomass. Biomass is the name given to any plant or tree grown to be used as a fuel. Wood burns in air, releasing heat energy. This heat energy can be used to produce steam to generate electrical energy. If new trees are planted to replace those burned as a fuel, biomass becomes a renewable energy source. Sugar can be fermented to produce ethanol, an alternative to petrol. The main disadvantage of the use of biomass is the large areas of land required to grow the plants and trees. Harvesting and production costs can also be quite high. Nuclear fusion. Nuclear fusion is the process that powers the sun. Fusion basically means to join. We are recreating this process on Earth because it gives us even more energy than nuclear fission, about 3 times more per kilogram, has relatively harmless byproducts, and the deuterium fuel required is abundant in our oceans. The 2 small nuclei hydrogen isotopes called deuterium and tritium, naturally found in the oceans, are pushed together so hard that they stick, fuse together. During this process they form helium, an inert gas, and the reaction produces enormous amounts of energy. Unfortunately, in order for these hydrogen isotopes to move fast enough and fuse, we need a temperature of about 50 million degrees Celsius. Scientists can achieve this momentarily, but are struggling to maintain the temperature for a sustained time. The EU, Japan, the USA, Russia, China and South Korea are collaborating together on a project named ITER. This is a €10 billion venture to create the world's first full-scale fusion reactor in France. The reactor will be used to develop the technology required to build commercial fusion reactors for electricity generation. Construction will start in 2007, and the reactor is due to be operational by 2016. Turning moments. A force may cause an object to turn or twist. This turning effect is called a turning moment. If the distance of the force from the pivot is small, the turning moment will be small. If the distance to the pivot is made larger, the turning moment is increased. Turning moment of a force equals force times perpendicular distance from pivot. Calculating turning moments. In the animation, a force of 100 newtons is applied to the spanner. The perpendicular distance to the nut is 20 centimeters or 0.2 meters. The turning moment produced by the force equals 100 newtons multiplied by 0.2 meters, which equates to 20 newton meters. This turning moment causes the nut to rotate anti-clockwise. The handle of a door is always placed on the opposite side of the door to the hinge. This maximizes the distance that the force applied to the handle acts from the pivot. The large turning moment makes the door easier to open. Balanced moments. The uniform beam shown is balancing horizontally, even though 2 unequal masses have been placed onto it. The 2 downward forces acting on the beam are 60 newtons and 40 newtons respectively. The 40 newton force is 1.5 meters from the pivot and produces a clockwise turning moment of 60 newton meters. For the beam to balance horizontally, the 60 newton force must provide an anti-clockwise moment of 60 newton meters and must be placed 1 meter from the pivot. So, for balance, total anti-clockwise moment about pivot equals total clockwise moment about pivot. Levers. We can apply the principle of balanced moments to levers. A lever is a simple machine designed to apply a force to move an object. The wheelbarrow shown can be used to lift a large load by applying a smaller effort. As we saw earlier, if the man exerts an upward force of 400 newtons, an anti-clockwise moment of 300 newton meters is applied at the pivot. The load must apply a clockwise turning moment of 300 newton meters at the pivot. If the distance of the pivot from the center of the load is 40 centimeters, the load lifted will be 750 newtons. Pressure. Pressure is the force acting over a given area. Pressure measures how concentrated the force is on a body. Calculating pressure. Two identical blocks of wood pushed downwards on a table with the same force. This force is their weight, 30 newtons. The two forces, however, are spread over different areas and will exert different pressures on the table. We can calculate the pressure exerted by each block on the table by using the equation pressure equals force divided by area. We can see that the largest pressure occurs when the force acts over the smallest area. The smallest pressure occurs when the force acts over the largest area. Calculating pressure. An elephant has a weight of 15,000 newtons. The elephant must have big feet to prevent him from sinking into the ground. The total area of elephant's feet is 0.24 meters squared. If the weight is spread evenly over each foot, then area of each foot equals 0.24 divided by 4, which equals 0.06 meters squared, 600 centimeters squared. Pressure and gases. The particles of a gas are in continuous rapid random motion. As a result, the particles collide with the walls of their container, exerting a pressure. The pressure exerted depends on the mass of gas present, the volume the gas occupies, and its temperature. If the temperature of the gas is increased, the particles gain kinetic energy and move more quickly. As a result, the particles collide with the walls of the container more quickly and more often. This causes the pressure to increase.